Hello and welcome to another power electronic class. We started today's class with a small quiz, and I'll post the quiz for online students as well. I'm gonna go ahead and solve this quiz. So the quiz is that we have the following converter, and the input voltage is 30 volts. The output voltage is 15 volts. So it's a buck converter because it's stepping down the voltage. And first we want to calculate dA, the duty ratio, and then we want to calculate the pulse width, or T on. So from the equation that is already provided, dA is V out over Vn, which is going to be 30 15 V out over 30, which is going to be equal to 0.5. So this is for the first part of the question. Now we will need to find the period Ts, which is going to be 1 over Fs. What is our frequency? It's 100 kilohertz, so it's going to be 1 divided by 100 kilohertz, or 100,000. So 1 divided by 100,000 gives us what? 10 microseconds. Now, we already know that the total period is going to be equal to Ts is equal to T on plus T off. And we also know that T on is equal to dA, or the duty ratio, times Ts, the duty cycle that it's turned on. Therefore, T on would be equal to dA, which is 0.5, times Ts, which is 10 microseconds, gives us 5 microseconds. And it's obvious, we have divided the output voltage in half. Therefore, 50% of the time it's going to be turned on, 50% turned off. So it's going to be turned on for 5 or more microsecond, and the off time is also 5 microsecond. And the average voltage would be in the middle. Is it clear? Can I go to the next slide? Okay. So today's class, we would do a review of semiconductor devices, which is a very important part of this, of the converters and switches. We learned that to convert DC to DC, best way to do it to have the highest efficiency is to use a switch. And obviously, when you have a switch that is opening and closing thousands of times per second, when you have 100 kilohertz, meaning it's switching 100,000 times per second, you can't do it with a manual switch. Okay, you need to have a control system and a semiconductor switch to do that. So switches are mainly made out of semiconductors. For the design of switching power poles, we have power semiconductor devices. And for those, we have uncontrollable diodes, uncontrollable systems, which are diodes. We have half controllable, or thyristors, which we usually show them like this. And we have controllable, which are transistors, BJT, bipolar junction transistor, metal oxide, MOSFET, IGBT, GTOs, and so on. And then we will study the losses in switching power pole, the switching losses, and also the conduction losses. We will do a quick review of semiconductor and how do these semiconductor devices work. The principles are the same for the diodes and transistors, all of them. We usually have a semiconductor, which is silicon or germanium. And we usually have an acceptor or donor, which is boron or phosphorus or arsenic or something like that. And this is, by the way, just a review of your electronic devices and circuits class. So semiconductor devices are electronic components that exploit the electronic properties of semiconductor materials, principally silicon, germanium, gallium arsenide, as well as organic semiconductors. Semiconductor materials can be easily manipulated by the addition of impurities known as doping. Semiconductor conductivity can be controlled by introducing of an electric or magnetic field to make excellent sensors. We have different type of doped. We have the N-type and P-type. If we introduce an extra hole or a positive charge, we will create a P-type. And if we introduce a negative charge or an electron, we create an N-type. Semiconductors on their own are not good conductors, but by introducing the extra electron or extra proton or holes or electrons, we can manipulate them and change their properties. This picture shows the semiconductor lattice. Semiconductors usually form a lattice like the silicon. They have very strong bonding. And this is a silicon, for example, normal silicon. And when we introduce an extra electron to the system, like when you bond it with the phosphorus is in the middle, there would be a free electron in the system. So this one has a donor electron. We have doped it with a phosphorus. Now you have made it an N-type or a negative type semiconductor. And if we dope the system with the boron is in the middle. Now we have an extra hole, which we create a P-type system. So an N-type and P-type on their own, they're good if you want to build a resistor or something and you want to, somehow be able to design the characteristics of a resistor. But on their own, we don't use them. What happens is when you connect these, you have very interesting properties, and what we call that a p-n junction. So if you have a p-doped and an n-doped semiconductor and you smash them together, you have an acceptor on one side, you have a donor on one side. The acceptor has a hole. The donor has an extra electron, and when we connect them together, it creates a zone which we call it the depletion zone. And what happens is initially when you connect the P and the N together, the electrons move from the N side to the P side, and the protons, and they leave behind a hole or a positive charge. So what happens is the electrons start moving to the P side, and you would have a small depletion region over here. And when they leave, they will leave a hole behind them. And what happens is this stabilizes. It doesn't continue at the end. And when you connect the P side to a positive, or the N side to an N negative, or the P side to a negative and an N side to the positive, something interesting happens. You create a one-way, like it's like a one-way valve. It acts like a one-way system, allows the current to pass in one direction and blocks it in the opposite direction. So what happens if we connect these to the positive end? You're going to saturate this with the positive. And when you connect this to the negative, you're going to saturate it with negative. And therefore, you're going to have a connection between them. But if you connect this to negative and connect this to positive, you're going to expand the depletion region and you're going to block the system. So a bipolar diode is created when we connect the PN junction. In forward bias, the positive is on the P side and the negative is connected to the N side. In the reverse bias, the positive is on the N side and the negative is on the P side. Again, forward bias, what happens when we connect the P side to positive and connect N side to the negative, so there would be a flow of current going, let's say, from positive to negative. But if I connect the P side to negative, and I'm going to show it with black, if I connect the P side with negative, all of these would be negative, and all of these would be positive. And I'm expanding this depletion region, therefore it would not allow any current to pass in the opposite direction. There are usually a small on-state voltage drop. For a silicon diode, it's 0.7 or 0.6. For germanium, it's 0.3, sometimes 0.4. And in the reverse bias, we have a small leakage current. And this is our forward and the VI, the current voltage characteristics of a diode. On the left, you would see a normal diode, a real diode, and on the right is an ideal diode. Okay. For an ideal diode, as soon as the voltage becomes positive, it starts passing the current through in forward bias, and it's turned on. And when the voltage is negative on it, it's going to be turned off. But in real world, the diode doesn't work like that. You need a little bit of voltage to be able to turn on the diode. And that voltage is called the forward bias voltage, or VF. And for a silicon diode, it's usually 0.7 volts. For an ideal diode, if the reverse voltage is even thousands of volts, it will still block the current flow. But in real diode, we have a breaking point. And after a certain point of reverse, depending on the diode, what happens is the diode, the PN junction, it collapses. You're going to destroy. It's like a valve that you're putting too much pressure on it when it's closed, and it's going to break. So this is the breaking point for the diode. And this region before the breaking point is called the reverse blocking region. This region here is the forward bias, or the conductive region. And in an ideal diode, actually it looks like this. It's the current in the reverse bias is not actually zero. It's little bit less. And the area under here is the leakage sensor, the leakage current. Meaning in reverse bias, if it's like a valve which is shut, but you still have a little bit of water passing by, a little bit of current passing. So in reverse bias, there is a small leakage current, and that actually causes a lot of problem, and sometimes a big part of the loss in a switch is the leakage current. Another thing that we have in the diodes is the reverse recovery. Usually the turn on off is very fast, but the turn on is very fast. But when you want to turn it off, it takes some time for the holes and for the electrons to move along the silicon and the semiconductor. So this takes time from going from forward bias to reverse bias, or from turning on to turning off. And that time is called the reverse recovery time, or TRR. And it's for the time it takes to restore the depletion region. Depending on the type of diode that we have, if it's a signal diode or a power diode, it could be from few milliseconds to nanoseconds. As mentioned, we have different type of diodes for different applications. We have Zener diodes, we have power diodes, signal diodes, and so on. For line frequency diodes, we have the line frequency AC to DC, which are usually used in rectifiers. The on-state voltage drop is 1 to 3 volts. The voltage blocking is up to 9,000 volts, meaning the reverse voltage, the breaking point here, is around 9K volts, 9,000 volts. And the forward bias voltage is 1 to 3 volts. The reason that we have 1 to 3 volts, usually you have multiple diodes. If you have a bridge diode, you would have 2 silicon diode, 2.7, it's going to be 1.4, something like that. And the current is up to 5,000 amps. Then we have fast recovery diodes, signal diodes. They are very, very high speed, up to several hundred kilohertz. And they have low switching losses. But the problem usually is you can't put a lot of voltage on them. Usually they are limited to a few hundred volts. You can't do 2,000-3,000 volts on them. And we have Schottky diodes, which they have a very low voltage drop of around 0.3 volts, which are usually made out of germanium, very fast as well. These are also used in electronic systems, not electrical systems. So you're all familiar with diodes. They are mainly used in rectifiers and bridge rectifiers. And diodes are uncontrollable, meaning you don't have any control on when to turn it on or when to turn it off. As soon as it's in forward bias, it's turned on. When it's in reverse bias, it's turned off. And if you have like a sinusoid signal coming from an outlet and you connect it to the diode, you can't turn it on, let's say, at the middle of the positive cycle. It automatically turns on around here and it turns off around here. So what you have in the output is this. But if I want to have something like this in the output, I cannot do this. So I have no control on when it triggers, it turns on and off. It's completely dependent on its input. There is a different type of system that we have in power electronics, which are half controlled systems. And the half controlled systems, we can control them in when they turn on, but we can't control them. We can't have any control on when they would turn off. They are called the thyristors. It's like a diode, but it has a connection to it. It acts like a switch again. It has the same characteristics as a diode, but the difference is you have control on when to turn it on. We turn it on by giving a signal to the gate pulse. We call it the gate pulse, or IG. It conducts in the anode-cathode direction. After being in forward blocking state, it latches on, and the gate signal need not to stay on. So you just turn it on, it would stay on. The forward voltage drop is usually 1 to 3 volts. We don't have any control on when to turn it off. So not controlled by the gate pulse. Turns on when the forwarding current has fallen small enough. So the way that it happens, imagine you have a signal like this. And when the voltage goes up 1 or 3 volts, and you have a current coming in, it turns on. So imagine we turn this on immediately, and the black one is turned on. As soon as it goes into reverse bias, it automatically turns off. So what happens if it's in forward bias, but the control signal doesn't come on? And imagine here we had the control signal IG. What happens if I have the signal and IG remains 0? What would we have in the output? The output would look like this. You won't have, technically you won't have any signal. If it's an ideal system, you won't have any signal in the output. So, and it automatically turns off when the input is in negative. So if I keep it on, if I keep this signal on, let's say I give it 20 milliamps or something like that, or a few volts. If I give it a gate signal at all time, it's going to act like a diode. And when it's a diode, the VI characteristics are exactly like the diode. So you can see that in on state, it acts exactly like a diode, like the previous graph that we had. We have the forward voltage bias, we have the leakage current, and so on. But when it's in the off state, you can see that it acts like the diode is in reverse bias. And we still have a forward breakdown and the reverse breakdown voltage, because you can't put, infinite voltage on when it's in reverse bias and forward bias. It's going to break down. It's going to destroy at one point. Now, for an ideal thyristor, it's again the on-off part is exactly like the diode, which I'm doing with red. But for forward blocking, we also have another one, which I'm going to draw with the green one, which looks like this. So a diode was like this, and a thyristor has this part. It's like a reverse T. That's for an ideal situation. And this is for a practical situation, real world. And you can see that this part is exactly like a diode. Okay. So adding a gate pulse to a diode, we create a thyristor. Now, a thyristor turn on looks like this. So Vs is our input signal. Let's say this is 100 volts or something like that. And this is the forward voltage VAK, and IA is actually when the thyristor is turned on. So it's going to be turned on. The thyristor I'm going to draw it with red. It's going to be turned on when it's on the red one. And when it goes to reverse bias, it automatically turns off. So you're not gonna see, you can see that IA is turned off when it's reverse bias. By the way, this is for an ideal thyristor with no leakage, but in reality, you're gonna have a small leakage, so a small current. But I'm just gonna follow example here and mention for an ideal. Is it clear? Yes? Okay. Now, the thing that we are interested in, and like 90% of the current converters are working with, are controllable switches. They are made out of transistors. It could be made out of different type of transistors, depending on the application that we want to use them for. Where do we use them? For what purposes? It could be the bipolar junction transistor, which was the first generation. They have made a comeback recently with some modifications. We have the metal oxide semiconductor or field effective transistor. We call them MOSFETs. We have the insulated gate bipolar transistors or IGBTs. We have the gate turn off thyristors or GTOs. We have the MOS controlled thyristors or MCTs. The good thing about thyristors, before I move on, is that they can operate in very high voltages. So for high voltage applications, they work pretty well. I've seen thyristors that are the size of that trash can. They are very, very large. Big cylinders that you would see. So you can scale them up, build them very, very large using these vacuum tubes and so on. But they are slower and they have some limitations. Now, as you remember, I'm just going to go back. I'm sorry, these are notes from last year. Erase them. So as you may remember from your electronic devices and circuits, and by the way, the principles of transistors for all of them is 90% the same. So I'm just going to go through BJT, which is pretty easy, and you already learned them. So for a BJT transistor or most other types of transistors, we have three terminals. We have the collector, base, emitter. For a MOSFET transistor, it was a drain gate source, for example. The gate or the base is the control for the system. I'm going to use the water analogy for this. So imagine you have a faucet. This is the drain or the emitter or the drain. And you have the gate or the base, and you have the source or the collector. And we have the faucet itself that controls the output, okay, which here could be for this analogy, it's water for output. So giving a signal meaning you're twisting the faucet and you're opening the valve. Transistors usually have three different areas of operation. We have the three different regions. We have the saturation region. We have the turn off region, which is down here. And we have the active region, which is in the middle. So turn on and off the red and the blue one. I'm going to do the active region with green one. What we are interested in power electronics. When it's in the saturation and the turn off region, the transistor acts like a switch. It's on when it's in saturation, it's off when it's in turn off region. When it's in the green region, it acts like it's usually used for an amplifier, like a common emitter, common collector, and so on. For a BJT transistor, for example, IC is equal to beta IB. So the beta, which is the important part, is equal to IC over IB. For a signal transistor, beta is like 50 to 100, something like that. And when it's above 100, we would assume that IC is equal to IB. For a power transistor, usually beta is 5 to 10, something like that. And we have another term as well, which is alpha, which is beta over beta plus 1. And IC is alpha IE. Again, if beta is large, like 100 or so, IC would be almost equal to IE. Again, if beta is greater than 100. So depending on different base currents, you can see here, we would have different currents in the output. So the higher the base current is, you are going to have more current in the output, obviously, because of this equation that you have here. So you can also write this as IE, but it's equal to beta IC. Or IC or IE, because the beta is too big. So the base current has to be kept on and sufficiently high. The current gain beta, which is IC over IB, around 5 to 10. This is used in low voltage and high current applications, so BJTs. A different type is the metal oxide semiconductor field effect transistors. Again, we have the gate, drain, source here. And these are better for power electronic systems, newer generation compared to BJTs for higher voltages. The voltage controlled device, VGS, is to control the ID or the drain current. The threshold voltage is around 2 to 4 volts. So it takes 2 to 4 volts to turn this on. And it has very fast transients, around 30 kilohertz or 30,000 times per second, or 1 million times per second, 1 megahertz. Again, we have the on-off region, and the higher the voltage, the VGS voltage goes, you're going to have a higher current in the output. So this is the output current. Imagine this is 10 amps, 7 amps, 4 amps, something like that, 1 amp. And the higher VGS is, you're going to have more current, ID, which is the drain current passing through. Then we have the GTOs, which is similar to a thyristor. The only difference is now we can control when it would also turn off. So instead of, do you remember for a thyristor, we had one-way connection, which was like this. For a GTO, we have a two-way connection. The GTOs turn on as with thyristors and turn off with a relatively large negative gate current pulse. The voltage and current ratings are large. Fs is not more than 10 kilohertz. So very large voltage, very large current, but low frequency compared to the MOSFETs. Can you give me an application for this one, the GTOs? Where do we need very high voltage, very high current, but low frequency? Yes, the power outlet frequency, which is 60 hertz. If we want to build an inverter, this is ideal. If we have like a 10 kilovolt, 100 amp system, high voltage, high current, this is going to be ideal for that. Cheap, and we don't have high frequency, we have relatively low frequency, which is perfect for that. And then finally, we have the IGBTs, again, another form of transistors. The GTO is also sometimes categorized as a sort of transistor as well. But IGBTs is similar to MOSFET in high impedance gate for small amount energy to turn on. It's similar to BJTs in low on-state voltage, 2 to 3 volts. The turn on and off delay is approximately 1 microsecond, which is great. The most common components in inverters for asynchronous induction motors and so on. So this is the most sophisticated one. It's a combination of MOSFET and BJTs. So it has the best of both worlds. And you can see for an ideal IGBT, it looks like the GTO. And for non-ideal, you can see it in a turn-on situation, it looks like a BJT transistor. And the turn-off situation, it looks like a diode. So it's a perfect combination of MOSFET and BJTs. High frequency, low reverse, low forward bias voltage drop, so higher efficiency and high impedance. Therefore, you're gonna need a lower current to turn it on as well. And then we have the MCTs, or MOS controlled thyristors. They're relatively new components, not widely used, very similar to GTOs. At turn off, only a small current pulse is needed. So the GTOs, you needed a very large pulse. Here, you need a small current to turn it off. The on-state voltage smaller than in a BJT, so it's more efficient. MCT so far is not doing great. IGBT seems to be more competitive. Now, switching in power poles, we have a IGBT connected. You can see the diode, which helps with freewheeling. And again, we can see that the on and off switch and the active region, when we give it a small voltage to its gate, we can control the ID current for it. So this is a more sophisticated version of the first one, the previous one that we saw. This graph shows the turn-on characteristics. So again, when we want to turn this on, we need to have a voltage coming into the gate. And when the voltage in the gate is applied, then ID from ideally going from 0, it goes from 0 to its maximum. And when it goes to the maximum, VDG goes from its maximum to its minimum. It's like a switch that it's been turned on. When the switch turns on, the current goes up, the voltage drops, because now VD and VG for an ideal situation are equal when it's turned on. Usually for the VGS, the gate source voltage, we need the threshold voltage, which is around 2 to 4 volts. And so, and depends on the type of transistor as well. Some of them are lower, some of them are higher, depending on when we use them. I also added a note here so you can read as well. So to turn the MOSFET on, the gate drive voltage goes up from 0 to VGG, and it takes the gate drive a finite amount of time called the turn on delay time, which you can see here. To charge the gate source capacitance through the gate circuit resistance R gate to the threshold value of VGS. During this turn on delay time, the MOSFET remains off and I/O continues to freewheel through the diode. So again, it takes a little bit of time to turn on, and then you can see the I/O is increasing and VDS is decreasing. So the voltage is dropping, and the voltage between the drain source and the drain gate as well. Sorry, V drain source. And it's the same for V drain gate as well. So V drain source would drop and therefore would be equal. So VDS becomes equal to 0. You can see here VDS is dropping to 0. Now a practice problem. In the circuit shown, Vn is 100 volts and I out is 10 amps. During the turn on of the MOSFET, the drain current has risen ID to 8 amps. If the diode forward voltage drop is VFM is 1 volt, what is the value of VDS across the MOSFET at this time? I will give you a few minutes to think on this in notes. Okay, does anyone have the answer? So if we go back to this graph, we can see that it takes a little bit of time for the transistor to be saturated. Therefore, we're going to have the diode still freewheeling in the system. And when the diode is still freewheeling, we have a 1 volt voltage drop in the diode. Therefore, the voltage, if we do a small KVL, we would see that the voltage going through the between these two, the VDS is going to be 100 minus the 1 volt from the diode. So we're going to have 99 volts on the transistor. When the transistor is turned on, you're going to have a 1 volt drop on the transistor. So the correct answer is 99 volts. Again, because haven't started, it's not in its saturation mode, so you're going to have a 1 volt drop over here. So it's going to be 100 minus 1, we're going to have 99 volts. And here you can see the turn off characteristics of the IGBT transistor. Again, we have an off situation. And when you have an off situation, the current goes from its maximum to its minimum 0, and the voltage goes from 0 or TD off. It takes a little bit of time to, so from going from 0 to on. On to off, which is its maximum. So Vn goes from 0 to its maximum. Okay, I think it's enough for today. Next week, we're going to start with the switching losses. And the week after that, we will complete the buck-boost converters. Thank you so much and have a great day.